Alright guys, so for the last 3 lessons of this summer work, I'm going to talk to you all about rational functions. And we see that we have 8 rational functions here in front of us. So rational function, rational means ratio. It means it's a rational function is the ratio of 2 other functions, and in particular 2 other polynomial functions. So if you look at question 1 here, we have a function a of x. A is a function of x, 2x squared minus 9 over x squared minus 9, for example. We notice that 2x squared minus 9 is itself a polynomial. It's a polynomial function. Taken by itself, I might have this as f of x equals 2x squared minus 9, for example. And similarly with the denominator of x squared minus 9 down here, that too is a polynomial function. But when we take the ratio of those 2 functions, 2x squared minus 9 divided by x squared minus 9, when we take the ratio of those 2, what we have is something quite different. We call that a rational function. And a rational function does not look at all like the function for 2x squared minus 9 would look by itself, or indeed the function of x squared minus 9 if I was to graph it, what that would look like all by itself. When you take the ratio, it looks quite different, and they are very interesting. So for like I say, the next 3 lessons, I'm going to talk to you about various aspects of rational functions, how we go about graphing them, and various interesting points that we can find, including the x and y intercept, and something that we're going to call asymptotes, which I will talk to you more about next week. All I want to do today is talk about the domain of a rational function. That's all, just the domain. And what the domain means is that is the list of allowable inputs. That is the values of x that we are allowed to put into this function. Now, if I have a polynomial function, for example, again, if I have a function 2x squared minus 9, right? If I have a function f of x is equal to 2x squared minus 9, which just so happens to be the numerator of question 1 there. Well, we all know that that is a quadratic. It's a quadratic binomial. There's 2 terms. The leading term is 2, so that's positive. So we know it's going to make a parabola, and it's going to open like that, right? It's going to make that distinctive parabola. It's going to open upwards. Being a polynomial, the domain, the list of allowable inputs, is negative infinity to positive infinity. In other words, you can put in any value of x that you choose into a polynomial, anything at all. So in that respect, polynomials are kind of a little boring when it comes to domain. The answer is always just negative infinity to positive infinity. Put in anything you like, not just for quadratics, but indeed of any degree polynomial that you choose. However, with rational functions, it's quite different. So let me just get rid of this here for a second and take down my function here. So I'm going to start with question 1. So I think it was a of x, and it is 2x squared minus 9 all over x squared minus 9, x squared minus 9. All right, so when we're going about graphing this and considering the domain of this function, what we need to be careful of is that in mathematics, we cannot have a 0 in the denominator. We cannot have a 0 in the denominator. So any values of x that would make your denominator 0 are not going to be allowed. Any values of x that would make your denominator 0 are out. They are not in the domain, and they have to be identified. How do we go about finding those values of x? Well, what we actually do is we let our denominator equal to 0 and solve. That's all we're going to do. And so I think you'll see that once we start doing 1 or 2 of these, you'll see that they're actually quite straightforward. So my denominator is x squared minus 9. And what I'm going to do is I'm going to let x squared minus 9, maybe I'll say, right, let x squared minus 9 equal to 0. You're going to do this every time. Let your denominator equal to 0 and then solve. All right, and so now you've got a relatively straightforward equation here to solve. What would I do? Well, I would add 9 to both sides. I would have x squared is therefore equal to 9. And because I have a square on the left-hand side there, I'm going to take the square root of both sides. The square root of x squared is x. And the square root of 9 is, plus or minus 3. Do not forget that plus or minus. That is very important. Plus or minus 3 when you take the square root. And so that's it. The values of x that would make my denominator 0 are plus 3 and minus 3. And because those values of x would make my denominator 0, give me a 0 in my denominator, they must be excluded. They are not in the domain. What is in the domain? Everything else. Everything else except minus 3 and plus 3. And so what it amounts to is, if I kind of think about like the number line here for a second, here's my number line, there's negative infinity, perhaps here's 0, here's positive infinity in this direction. And I have, let's say here is negative 3 and here is positive 3, right? Number line goes from left to right, getting larger. Everything coming in here, everything here is coming in, everything is allowed, all of these values, all the way up to minus 3. Minus 3 has to be excluded. Negative 3.0001 is fine. Negative 2.999 is fine, but not negative 3 exactly. So negative 3 has to be excluded, I should say, from the domain. And then to the right of negative 3, everything's fine. It's all fine. All of this is fine right up until I get to 3. And then 3 must also be excluded from my domain. 2.99999 is fine. That's in the domain. 3.00001 can be in the domain, but 3 exactly cannot be in the domain. And then everything to the right, all the way out to positive infinity. And so to write that, the way we write this in our notation is we say our domain is negative infinity, and I have what I call a soft bracket there to the left of negative infinity, to negative 3. And now next to my negative 3, I'm going to put this hard bracket right there. And the reason I'm putting in that hard bracket is because that indicates that negative 3 is not part of the domain. And now I have to keep going. To the right of negative 3, I have a union. Negative 3, again, note that hard bracket because that tells me that negative 3 is not in the domain, to positive 3. And again, I have a hard bracket because positive 3, the hard bracket is next to that positive 3. Why? Because positive 3 is not part of the domain. And then finally, I need to go to the right of positive 3. And so I have hard bracket, positive 3 to infinity. And I always have a soft bracket I'm going to call I like to choose to call it a soft bracket next to my infinity or my negative infinity. And that's it. That's my domain. Negative infinity to negative 3, not including negative 3. Negative 3 to positive 3, not including negative 3 or positive 3. And then finally positive 3 to infinity, again, not including positive 3. That is my domain. And that is how I write it. A little awkward, perhaps, but that is at least one way that we can write it. All right, so that's that first problem. What I'm going to do is I'm going to skip on a little bit. I'm going to do questions 3, 5, and 7, and then I'm going to leave you to try the even number problem. So I'm going to skip on to number 3. It is c of x, and down here, c of x is equal to x plus 3 over x minus 3. X plus 3 over x minus 2. All right, there it is, a rational function. Again, note that I have if you like, a linear polynomial in my numerator and a linear polynomial in my denominator. But now I have to take the ratio of those, and so I have a rational function. How do I find the domain? It's the domain that I'm interested in today. How do I find the domain? I simply this is the same every time. It's going to get a little boring. Let my domain, not my domain, what's wrong? Let my denominator, let my denominator equal to 0 and solve. That's what you're going to do. All right, so my denominator is x minus 2. So I'm going to let x minus 2 equal to 0 and then solve. Well, that's very straightforward, even much more straightforward than our previous example. X minus 2 is equal to 0. Well, to solve this, simply add 2 to both sides and I get x equals 2. And this time, in this particular rational function, the only thing that is not allowed is 2. Everything else from negative infinity all the way up to 2, right up to it, is fine, is in the domain. 2 is not. And then everything to the right of 2, positive 2, is also in our domain. And so how do we write that? Well, our domain then, the way we like to write this is negative infinity to 2, hard bracket next to my 2 because 2 is not in my domain, union 2 to infinity. And I have soft bracket right there, parentheses if you like, next to my infinity, and that's it. That's all I have to do. That's my domain for c of x, x plus 3 over x minus 2. And again, next week I'm going to talk to you about what that means when we're graphing our functions. What does it mean when that 2 is not there? Okay, so moving on, see the e of x. Put a line here. So e of x is, it's a long one, 2x minus 1 over x plus 2. Sorry, 2x minus 1 times x plus 2. All over 2x plus 3 2x plus 3 all over 3x minus 4, all over 3x minus 4. All right, there's my rational function. This one is rather interesting. It's already, my polynomial, if you like, in my numerator and denominator has already been factorized. So that kind of makes my life a little easier, actually, even though some students might look at that and might think it's maybe more confusing, because actually it has made your life easier, the fact that they have factorized your numerator and your denominator already. Of course, for rational functions, and specifically for the domain of a rational function, it's the denominator that we care about. So what I'm going to do is I'm going to let my denominator equal to 0. So again, that is, I'm going to let 2x plus 3 times 3x minus 4, I'm going to let that equal to 0. I'm going to let my denominator equal to 0, and I'm going to solve. All right, well, how do I solve this? Well, what we say mathematically is that if you multiply 2x plus 3 times 3x minus 4, so if you multiply this times this and you get 0, well then either this is 0 or this is 0. And so what we're going to do, our solutions then, is that we take these one at a time, and we say, all right, well then either 2x plus 3 is equal to 0, or 3x minus 4 is equal to 0. If you multiply these two things together and you get 0, then one or both of them must be 0. So either 2x plus 3 is equal to 0 or 3x minus 4 is equal to 0, and now we solve these individually. If 2x plus 3 is equal to 0, then 2x is equal to negative 3, subtracting 3 from both sides, and now I divide both sides by 2. So therefore x will be equal to negative 3 over 2. And that's one of my solutions right there. That is one solution. If 3x minus 4 is equal to 0, then adding 4 to both sides, 3x is equal to 4, and therefore x is equal to 4 over 3, and that's my other solution. And those are the two values that are now not in my domain. Those are the two values of x that must be excluded from e of x. I could not take, for example, I have e of x there, I could not take e of negative 3 over 2, or I could not take e of 4 over 3. Those values of x would give me a 0 in my denominator, and therefore must be excluded from the domain, or not in the domain. Again, how do I write this? Relatively straightforward. These are the only two things that are not allowed. So I have negative infinity. I'm going to, on my number line, coming from left to right, I'm going to come across negative 3 over 2 first. I'm going to hit negative 3 over 2 first, so it's minus 3 over 2. And then I have what I call a hard bracket, union, negative 3 over 2, to the right of negative 3 over 2, through 0, 1, and then I hit 4 over 3. 1 1/3. And that also has a hard bracket next to it. Why? Because that's being excluded. And then union, finally, 4 over 3 to infinity. And that's it. And if you like, you could even put a plus there to indicate it's positive infinity. And so that's our domain. That's how we write it. So there are two values of x that therefore must be excluded. All right, last one. This would be g of x. And let's see what I have for g of x. I have x squared minus 4, x squared minus 4, all over 3x squared plus x minus 4. 3x squared plus x minus 4. All right. Again, I have a quadratic binomial in my numerator, and I have a quadratic trinomial in my denominator. For the sake of domain, it is the denominator that we care about. And so what I'm going to do is I'm going to let 3x squared plus x minus 4, let that equal to 0, and solve. All right. So I have a quadratic trinomial, and when I'm trying to solve quadratic trinomials, as we've seen in the past, I need to either factorize it, and if I find that I can factorize it, well, then I'm going to have to use maybe my quadratic formula or something like that in order to solve a quadratic trinomial. So let's try and factorize it first. It's typically the easier option, and so I like to start there if I can. So to factorize this, I have a 3x squared, so that would of course give me a 3x and an x. Note that I have a negative 4, so it's a negative here, a negative in front of my constant. And so that means that I'm either going to have a plus and a minus, or a minus and a plus. And so let me try minus plus. And let me go with, you know what? I'm actually going to try plus minus. I'm actually going to reverse that order. Plus minus, am I right? So let me try 1 and 4. That would give me x. No, that's definitely not going to work. So let me try something else. Let me try 4 and 1. 4x. Oh, okay, I think I'm on a winner now. And note that I have 4 and times 1 is, or positive 4 times negative 1 is going to give me that negative 4. And if 4 times x is 4x, and then minus 1 times 3x is negative 3x, and 4x minus 3x is plus x, and that is that central term right there. That's the one I'm looking for. And so I have factored it correctly. I have 3x plus 4 times x minus 1. That is the factored form of my denominator. And so what I'm doing is I'm letting 3x plus 4 times x minus 1 equal to 0. Now I can solve it because I have factorized it. You see the importance of factoring. It's the factoring that allows us to solve our quadratic. So I have, just as I did in the previous example, I'm going to take these one at a time. If I multiply this times this and get 0, well, therefore, individually, either 3x plus 4 is equal to 0, or x minus 1 is equal to 0. If 3x plus 4 is equal to 0, then solving this, 3x is equal to negative 4, subtract 4 from both sides, and then to isolate the x, divide both sides by 3, and I get negative 4 over 3. That is one solution. That is one value of x that would make my denominator equal to 0, and therefore it is not part of the domain. Over here, x minus 1 is equal to 0. Well, this is simple, one step. Therefore, x is equal to 1. You simply add 1 to both sides. And so I have one solution, two solutions. Those are the two values. The negative 4 over 3 is to the left. If you like, it's lower, it's a smaller number than 1, it's a lesser number. And so when I'm writing my domain, that's going to come first. That I'm going to have negative infinity to negative 4 over 3. Bracket, union, well, I need to go now negative 4 over 3 all the way to 1. And again, 1 is excluded. And then finally, union 1 to positive infinity. Again, I always have that soft parentheses next to my negative infinity and my positive infinity. And that is my domain. My domain is everything except for -4/3 and +1. All right, so I leave you to just find the domain of those remaining rational functions, 2, 4, 6, and 8. Again, you see that what it involves is simply letting your denominator equal to 0 and solving it, and then just writing it in that interval notation that you saw right there over and over again. And like I say, next week we will talk about what it means when you're for these values of x to be excluded and what that means for your graph. All right, very best of luck.